Next, we're going to have Brad Trib from the Rawlins Field Office in Wyoming talking to us about assessing effectiveness of resource management plans.
Great, thanks, Scott. Wow, people actually came back after lunch. That's awesome. Yeah. Pretty shocking on the last day, but I'd like to first thank my co-authors on this presentation. Cheryl Newberry, she's a rangeland management specialist in the Rawlins Field Office, and Scott Miller from the NOC. Today we've heard a lot of the different applications for the AIM protocol throughout the BLM, and so in 2008, the Rawlins Field Office Resource Management Plan was signed with very little to no measurable variables, which when I was talking to Scott about this, I said, I don't want to present because we don't have anything to present on. And he said, well, good news is most RMPs don't have any measurable variables. So here I am. So Cheryl and I in 2015, we sat down and we decided that we were going to implement the AIM program to assess the effectiveness of our RMP. And it's been about 5 hours since Emily went over this in detail for us. So just a quick overview of FLIPMA and that it's directing our AIM protocol. And, it just specifies the need for us to manage for multiple use, preventing undue and unnecessary degradation. And resource management plans play a really critical role. Just a quick overview of where we're located, south central and southeast Wyoming. The Rawlins Field Office encompasses approximately 3.5 million surface acres. We have just over 600 kilometers of perennial streams and rivers, and it's a really diverse field office. Anything from high montane forests that are often located within wilderness study areas to sagebrush steppe-type desert ecosystems. We have a wide range of moisture, anywhere from 6 to 16 inches a year, and we have many diverse stream types within the field office. So specific to the field office, where I'm a fish bio, some of the priorities in our RMP are cold and warm water fisheries management, things like Colorado River cutthroat trout, flannelmouth and bluehead suckers, and habitat for other aquatic dependent species, things like amphibians and various bird species, and other priorities like ecosystem services, things like flood control, clean drinking water, water for cattle and other domestic livestock. But under the multiple use mandate within these same watersheds, our RMP permits activities such as energy development like oil, natural gas, wind, and uranium, as well as things like grazing, timber harvest, and recreation. So relative to their availability on the landscape, our freshwater resources are disproportionately used. So good monitoring data is really needed to ensure sustained yield, which, like we've covered, is required by FLIPMA as well as other BLM policies. So in the field office, we took from a natural resource standpoint, we took a two-pronged approach, and we're looking at some terrestrial sites as well as an AIM, or an aquatic perspective. And we're looking at, and you've all seen these throughout today, all these land health standards, 1 through 5, they've been covered a lot today. And so it's no different in the Rawlins Field Office, and we're looking at things like healthy soils, healthy plant communities, habitat for the greater sage grouse, aquatic species and their habitats, as well as good water quality. And for the purpose of this talk, I'm going to largely focus on our aquatic assessments. Our ultimate goal is to integrate our aquatic and terrestrial monitoring, and we're well on our way. So our RMP relies heavily on land health standards. And so from a monitoring perspective, we sought to assess land health standard attainment across our whole field office. Specifically for aquatics, this includes land health standard 2 and 5. And the first objective up here is going to be the major focus of today's talk. But we are also working to identify biological impacts and observed stressors to understand land uses contributing to observed conditions. So how were our sites selected? First, we needed to select streams and rivers from about 600 kilometers of streams on BLM lands. And we sampled about 56, or we did sample 56 sites over a 2-year period. And just a quick breakdown on that, like I said, we have just a little over 600 kilometers of perennial streams and rivers in the field office. So 70% of that 600 plus kilometers were order 1 and 2 streams that we classified into small streams. And orders 3 and 4 were large streams, and order 5 was, we classified them as rivers. So since 70% of our stream kilometers are small streams, 70% of our 56 sites were sampled on small streams, so 42 total sites. And then it just breaks down from there. So 20% on large streams and 10% on rivers. And so what did we collect at these sites? And I mean, I'm just hitting buzzwords that we've already talked about all day. So just we looked at a suite of physical, chemical, and biological indicators. And, you know, each stream segment was at least 150 meters long. And so how did we make sense of the collected information relative to our RMP objectives? Like I mentioned before, the Rawlins RMP does not include measurable objectives, indicators, or benchmarks. So BLM land health standards were used to assess conditions. We characterized typical using a network of reference stream reaches sampled by the EPA and other agencies. So this is a really busy slide, and I'm going to combine our 2-day benchmark training into one slide. So strap in for the ride. This is a really important slide to understand really the rest of the data. So we took 286 reference sites from across the West for each of our indicator of interest. Things like percent fines, macroinvertebrates, bank cover, and the list goes on. From those sites, we then developed benchmarks from the reference site data. We use specific predictions using models or a range of variability approach. For example, if your sample point lies within ecoregion A, 30% or less of the 210 particles collected from that site must be 6 millimeters or smaller. And just to go into that just a little bit, that was just one of our variables and how we measured it. Pick up a piece of a rock or fine sediment, and it had to measure 6 millimeters or smaller to be considered fine sediment. So, so if it was less than 30% in region A, it classified as minimal departure from reference, which you've all heard that term today, minimal, moderate, and major. It's pretty AIM-heavy talk, but it really means it wouldn't flag as a potential issue. So step 3, we then rated each site by the indicator using the benchmarks. For example, at site number 3 in ecoregion B, right here, we had a fine sediment value of 85%. Well, the benchmark was 75% for major departure from reference. So for the fine sediment for site 3, it would be classified as a major departure from reference, or as a flag as a potential problem. So the last step, we took all of our indicators and we were able to make some condition ratings based on stream kilometers in our field office. And it goes back to our randomized sampling design. So now we're able to say with 90% confidence that 50% of the streams in this example have major departure for fine sediment in our study area. Hope you got that, because here we go. So how are conditions looking throughout the field office? So for water quality, I'm just going to give you two examples, pH and specific conductance. You know, for pH, a majority of our values fell between 7.5 and 8.5 standard units, which is pretty typical for western arid rivers. And it did not fall outside the range of benchmarks for major departure. So a large majority of our stream kilometers are in good condition or minimal departure from reference. So because of our random sample design, once again, we can say with 90% confidence that 74% of the stream kilometers within the Rawlins field office have minimal departure from reference, meaning pH values are in good condition, and they aren't flagging to me as any potential issues. In contrast, for conductivity, we see a much greater proportion of stream kilometers with major departure from reference. What does that mean? Well, if we look at the box plot, we can see that a quarter of the streams lie outside of our range of 500 microsiemens per centimeter. And some of these sites are 6 times greater, or well, one of the sites is 6 times greater than the upper level of 500 of that 500 units. So that is going to flag really high and be a big time concern to me. Why are we 6 times greater than what the max already should be? So in addition to some of the classic water quality indicators, we also looked at things like fine sediment and biological condition. For fine sediment, we observed approximately a third of our stream kilometers with minimal departure and about 50% with major departure from reference. It should be noted that we are still working to refine the benchmark for this indicator, but the range of values does suggest a fair number of streams are dominated by fine sediment. The trick here is going to be to ensure we are separating natural fine sediment loads and human-caused sediment loads. So for our riparian standard, once again, I'm going to share two out of the, well, I'm going to share two of the indicators, percent bank overhead cover and floodplain connectivity. So here I'm showing percent overhead cover as it is compared to the reference. Approximately a third of our stream kilometers in each of the 3 categories suggests we have streams with adequate shading, like the picture on the left. And the picture on the right has us asking, how can we create some more bank overhead cover to get things like cooler water that would potentially support better aquatic life. Lastly, under the riparian standard is whether streams have access to their floodplains. We observed the overwhelming majority of our streams exhibit minimal departure from reference and have good floodplain connectivity. It's really important to note, though, that many of our systems have experienced historic downcutting, and in the last couple of decades have created their own inset floodplains, which is shown here on the right. So here we organize from highest to lowest percentage of indicators with major departure from reference within our field office. Overall, some of the challenges identified in the Rawlins field office related to water quality and riparian conditions include things like fine sediment, excessive nutrient and salt loading, and increased riparian vegetative cover. But with priority stressors identified, we wanted to identify which indicators adversely affect aquatic biota. And to me, this is really the so what. So what that you have high conductivity, so what that you have a fine sediment problem. And so our objective was to relate water quality and in-stream habitat and riparian conditions to biological conditions which are indicated by benthic macroinvertebrates. So under the Clean Water Act, many of the systems in our field office have aquatic life support as a specified beneficial use. So understanding which stressors or indicators are detrimental to in-stream biota is a real priority. And the graphic is just an example, but it shows that based on measured chemical and physical conditions, that total nitrogen, phosphorus, salinity, or pH, we would expect reductions in biological conditions. And so that just leads us into some of our data that we're just starting to get into on this. And so our preliminary analysis show that we can explain almost half of the spatial variability in macroinvertebrate scores with 4 of the measured indicators: percent fines, large woody debris, conductivity, and nitrogen exceedance. And as this example shows, you can see the relationship that fine sediment and macroinvertebrate scores, when it hits about 60 to 65% fine sediments, you can see our macroinvertebrate scores just tank. And so what are our next steps? We integrate terrestrial and aquatic monitoring. How are upland conditions influencing stream and river conditions? What surface disturbances or land uses associated with departure from reference conditions? What adaptive management strategies could be implemented to improve conditions and where? And how are conditions changing through time? And some of these, we're tackling now, and others, it may take us a little bit of time to get to some of these, but that's just some of our next steps. And with that, I'd take any questions if we have time.